learning for resource assignment in virtualized radio access networks. We are witnessing an exponential growth in both data traffic and number of connections in mobile networks. To accommodate these ever-increasing demands, more base stations have to be deployed, enabling spatial utilization, higher capacity, and lower latency. However, the network densification implies the increase of the operational cost. Radio access network virtualization, vrAN, is a key technology envisioned to reduce the cost by enabling resource pooling via centralization, easy updates via softwareization, and the most important, cheaper deployments. However, now we wonder, how do we allocate the resources in virtualized radio access networks? We will show it with an example. We have a variable traffic intensity in mobile networks. So previous approaches overdimension the use of the resources to cope with peak demands. We propose an adaptable use of the resources as a function of the network requirements, which can reduce the operational costs. However, this resource assignment is very complex because it depends on many factors such as the user demands, the channel conditions, and the CPU platform. We will show it to example. This figure shows the percentage of the served throughput in a virtualized base station. The x-axis indicates the CPU time, and the y-axis indicates the radio configuration. If we choose the wrong combination of CPU and radio configuration, we will fall in the dark area, which means almost zero throughput. And our objective is to maximize the throughput. However, this is not that simple. This figure is the same as in the previous slide, but for different channel qualities and for different CPU platform for the virtualized base station. We can see that the shape of the good performance area depends on these variables. The same occurs when we change the traffic patterns. So we can conclude that the performance of the virtualized radio access network is a very complex function of the context and the resource assignment, motivating the use of deep learning. Now we will present our AI-based resource controller. The input of the resource controller are the context in terms of channel quality samples and data arrivals. These contexts are sent to the resource manager, which computes a CPU orchestration and radio orchestration controls. These controls are the maximum CPU time and the radio configuration. The virtualized base station receives these controls, and based on that, it operates. At the end of the orchestration period, some performance metric are obtained. Based on this performance metric, we compute the reward. The reward allows the resource manager to operate and learn for the next orchestration period. In this figure, we can see the implementation of our virtualized base station using SRS-LTE, a well-known software implementing the full LTE stack and Docker containers. Now we will show the implementation of the resource manager, its challenges and solutions. The first challenge is the dimensionality of the input context, since we consider a large amount of samples in terms of channel quality and data arrivals. To solving that, we propose the use of 3 sparse autoencoders to reduce the dimensionality of the input. The second challenge is the heterogeneity of the action space, since for each base station we have a CPU control, which is a continuous value, and a radio configuration, which is a discrete value. We propose to decouple the radio and CPU policies. And for the radio policy, we use a deep neural network classifier that for a given CPU control and an input context, it computes the radio controls. Finally, the third challenge is that we have n-dimensional continuous controls for the CPU policy, where n is the number of virtualized base stations. we propose the use of a reinforcement learning algorithm called Deep Deterministic Policy Gradient, which learns the complex relation between the input context and the n-dimensional CPU controllers. To implement this reinforcement learning algorithm, we use an actor-critic architecture with neural networks. You can find out the results in the paper. One virtualized base station and unlimited to minimize the costs while satisfying the quality of service. These are the contexts in terms of traffic load and channel quality. This represents a very dynamic scenario, which is a worst case. These are the vrAIn CPU allocation for high, medium, and low quality of service. We can see that for lower quality of service, less CPU is allocated. And here we can see the trade-off between the average CPU savings against the quality of service. The lower the quality of service, the highest the CPU savings. Now we will evaluate a second scenario with limited CPU resources. In that case, we consider 2 virtual base stations and 1 CPU. Both virtual base stations have to compete for this resource. In that case, our objective is to maximize the performance of both virtual base stations. These are the contexts for both virtual base stations in terms of channel quality and traffic load. And these are the vrAIn policies in terms of CPU allocation, and radio configuration. We can see that for similar contexts, vrAIn assigns similar CPU, and the opposite. For diverse contexts, we have different CPU allocations. We can also observe that when we have high aggregated load, the radio configuration is reduced. This avoids the coding error. So thanks to this radio configuration reduction, vrAIn achieves 0 decoding error. We use, in this work, a novel combination of the reinforcement learning, sparse autoencoders, and neural network classifier to solve the problem of resource allocation in virtualized radio access networks. Our solution minimizes the CPU cost over 30% with unlimited resources and increases the throughput over 25% with limited CPU resources with respect to the state-of-the-art solutions. We use real data that you can find online following the link in our paper, and we presented our demo on Thursday. You will have the opportunity to see our demo again tomorrow in WeTech workshop. Thank you very much.